So I think we can just start slowly, Cordian. I think some people are still joining, but it is time. So it's my great pleasure to introduce once again Dr. Cordian Riener for the third and last part of his lecture series on symmetries in real algebraic geometry. And this, of course, is a part of the POEMA Online Learning Weeks. And I think most of the participants have been here before, but in case you haven't, just remember, if you want to ask a question, just type to everyone in the chat box, and Cordian can read these questions and will answer them when he gets a chance. So without further ado, the floor is yours, Cordian.
Thank you very much, Etienne, and thank you everybody for joining in this last session today. And as this is the last session, I will also use this to wrap a little bit up, but also to give you a new perspective or a different perspective to some extent of what we have been seeing in the previous lectures. And in this last part, I want to focus on something that I called orbit spaces, which we will define later. And I hope that this makes all sense, even if you have not been here before. But let's see. I have to just check how. Okay. Okay, so on the one hand, I want to talk today about the geometric side of invariant theory, namely this is what I call the orbit spaces. And on the other hand, in the second part or the end of the lecture, I want to make some cool present some, I think, cool results on the topology of these orbit spaces, again in the very special case of the symmetric group that we have been looking at for the previous lectures, also as a toy example always. And again, throughout the talk, we will have a group G that I will assume to be finite. And I will assume that this group acts on either Cn or Rn, so on the real vector space or on a complex vector space via a linear representation. Okay? Okay, and as a small reminder, what we had seen last week, which is one of the core results in invariant theory, was the following theorem. Whenever we have a finite group B, then we can look at the invariant ring. So this is the polynomials that are left invariant by the group action. So when the group acts on the linear vector space, we can also define an action on the polynomials. We defined this last week. And those polynomials who are fixed, they are called invariant polynomials. And the invariant polynomials form a ring which is finitely generated, finitely many polynomials. That means that we know that every invariant polynomial f can be expressed after we have chosen generators that might be, that they're not unique in general. We have to choose them. We choose the generators pi1 to pi m. I will always use pi today to denote these generators. Then we can find a polynomial g such that f is g evaluated at pi, 1 to pi m. Okay. Note, we also discussed this briefly last week, that this representation does not have to be unique. So even after we have fixed pi1 to pi m, the g is not necessarily uniquely defined. And there might be two polynomials, say g1 or g2, that have the same representation. Yeah? But then we just look at the difference of the two. So we define a polynomial h, which is supposed to be the difference between g1 and g2. And this then gives us an algebraic relation between the pi1s to pi m. So I just see here, of course, this should be pi1 to pi m and pi1 to pi m. At some point, I had started to use f, but then I figured out that this is too confusing. So I switched to pi, and yes, that's what happens if you change your mind in the middle of things. You forget that you also should do it in the beginning, of course. So we have these algebraic relations. And of course, any element in the invariant ring is thus only defined up to such algebraic relations. Okay? So if we denote the fundamental set of invariants, I call this fundamental set of invariants, with a big letter pi. So pi is just the set pi1 to pi m. or in fact, it shouldn't be maybe the set, it should be really the order tuple, pi1 to pi_m. Then I can define the ideal, I pi, or I mean just a set, all the polynomials that when you evaluate them at pi1 to pi_m, they're 0. That is the set of algebraic relations amongst pi1 to pi_m. Okay? Well, I mean, I already gave away half of the next sentence. I already called this an ideal. That's why I use conveniently the letter I. This is an ideal in the polynomial ring. And moreover, it's in fact a prime ideal. And you might want to check this. It's basically just calculations. And now whenever I have a set of polynomials, I can define a homomorphism, which is the evaluation homomorphism. That's also a general concept. I mean, I just evaluate pi by saying at the polynomial g, I just mean I take g and I plug in pi1 to pi_m. Okay? So, if I fix a set of generators, pi a set of generators of this polynomial ring of invariance, then we know that this homomorphism maps the polynomial ring in y1 to ym to the invariant ring, yes, and the kernel is exactly the ideal I. Thus, by the first homomorphism theorem, we essentially get that this polynomial ring, we get that this, we get that our polynomial ring, our invariant ring is isomorphic to the polynomial ring in y1 to ym modulo the ideal of relations that we have. Okay? So let's try to get a more geometric picture of what's going on. Okay, so again, I look at the relation ideal I pi, and I mean, for every ideal, I can define a variety. This is the points where all the elements in the ideal are 0. And because I have polynomials in m variables, this will be a set of c to the m. And the following thing actually holds. So this variety is in fact the smallest variety that contains the parametrization y1 equals pi1 of x1 to xn up to ym equals pi_m to x1 to xn. It is in fact the vanishing ideal of our variety pi_i, so in particular it's radical. And the variety that we have is in fact an irreducible variety. And if you look at the coordinate ring of this variety, then there is a natural homomorphism, isomorphism between this coordinate ring and our invariant ring that we just set up in a natural way. Okay? This is a little bit too much algebraic geometry language. Just think about, I mean, this just means that I have a system of equations, y1 to ym, that I want to solve for x1 to xn. And the points in the variety, they are exactly my solutions. Okay? Now let's come to what I call the orbit spaces. So when I take a point in Cn, I can look at its orbit GA, which is just all the elements that are reached from A by having G act on A. So this is all the points that are of the form G of A for some G in G. Okay? And the set of all these orbits that we just denote Cn modulo G, and this is the orbit space. And I mean, why does this modulo notation actually make sense? Well, I mean, we have this action on Cn, and this defines a natural equivalence relation by just saying 2 points are equivalent if they are in the same orbit. So if B is G of A for some G in G. Okay? So what is the important theorem now? The important theorem is that whenever I have a finite group, have this finitely many generators, then I can look at a polynomial map pi, which is the map from Cn to the variety that is defined by these algebraic relations that the pi satisfy, which is just taking a point in Cn to the evaluation of the pi's at A. So I map A1 to AN in Cn to pi 1 of A, A1 to AN, to pi m to, of A1 to AN. Yeah, so this is a map from Cn to some algebraic subset of Cm. And the important part of that is that this map is a surjection. So it covers all of the points in the variety. And in particular, we can define a map that takes a G orbit, Ga, and maps it to the point Pa, by just taking a representative of this orbit and using the map pi. And this, in fact, gives us a bijection between the orbit space to this variety V pi. So in some sense, we can think of Cn modulo the group action as rather, I mean, I can, at the orbit space, so this is all the orbits, I can identify the orbits with points in this variety. And in fact, all of the points in this variety are of this form. That's what this theorem tells us. Okay? So what is useful about this theorem? Why did I present the theorem? So in fact, a lot of the things that we have been doing aimed to the question how we can translate or transform questions that have some invariance into an easier form. And in that sense, we transform them into the orbit space. Let me just make this with this rather silly proposition clear. So I start with some polynomials that are supposed to be invariant. And in fact, I'm sorry, this should be now really complex polynomials. I'm sorry for that. So these should be complex polynomials, and this should be also complex polynomials because we only had the theorem for the complex numbers for the moment. Then I mean, the relationship between the fi's and the gamma i's is just that fi of x is just gamma of pi 1 to pi m of x. And then what we see from the previous theorem is just that if we have a solution of the system of equations, f1 of x equals f2 of x equals fm of x equals 0, then we need to have also a solution of the system gamma 1 of y equals and so on to gamma 1 of gamma m of y. And only if we have a solution to this other system will we find a solution to the previous system. So in particular, we can translate the solvability of such a system to the solvability of such a system. And in particular, this is then phrased in the ring that we have as the coordinate ring of our invariant, so our invariant ring. And in particular, for example, we can now, if you are familiar with that, use Hilbert's Nullstellensatz to certify that this polynomial system has a solution or has non-solution, and this would then immediately imply that we get a certificate for the above system too. And again, the gain might be that these polynomials might have much higher degree. These polynomials might have higher degrees. So these polynomials, the gammas, might have lower degree in, and this is the drawback now, potentially more variables maybe, but still it may be beneficial to prove that this system doesn't have a solution to conclude that this system will not have a solution. Okay? So let's just look at this rather maybe, I mean, I wouldn't call it complicated, but maybe rather ad hoc theorem in a very easy situation of the symmetric group again. So if we take the symmetric group Sn, what can we think of when we think about this theorem? So the important, maybe interesting first step is that we identify, to get this nice visualization here, we identify a point x in Cn with the n roots of a polynomial f. Well, I mean, how do we do this? Well, we just define f to be the product of these linear forms, linear factors t minus xi. So t minus xi is a polynomial in t. It's a polynomial in t with coefficients that are themselves polynomial in the small x's. We don't care about this. So we know we can write this in the form f to the n minus e1 of x, where e1 is the sum of the e's, tn minus 1, and so on, to en of x, where this is the product over the coordinates of x. So these EIs are the so-called elementary symmetric polynomials. And we have, if we forget about the x's, if we treat the x's just as some fixed parameters, we have a univariate polynomial in T. So what has this to do with the group action? Well, I guess you all agree that, I mean, the way I set up this product here, I essentially do not care too much about the order that I put the x's in. So, I mean, I could just flip all the factors in this product in any arbitrary way and get the same result back. Yeah? So this definition here is only, I mean, unique up to the action of the symmetric group on the coordinates of x. Yeah? And this is obviously visualized in the other form that we have here, because obviously these elementary symmetric polynomials are called elementary symmetric polynomials because they don't change if I have the symmetric group act on them. Yeah? So in fact, what we have is we have a surjective map. Why is the map surjective? Well, we know every polynomial of that form, every polynomial every univariate monic polynomial in the variable t of degree n has n roots. Yeah? So to every element here, to every selection of the e1 to en, I can find a pre-image x1 to xn, which is well defined only up to the symmetry action. So we have a surjective map from Cn to Cn that just identifies x with the evaluation of x at the elementary symmetric polynomials. And of course, this is constant on Sn orbits. So the ring of invariance is isomorphic to the ring that is generated by these elementary symmetric polynomials. And in fact, this is nothing else than the coordinate ring of the image, which is the orbit space. Okay? I have a quick question. Is the number m in page 6 of slide, let me just go back to see what you mean in slide 6, page 6 and 7. No, it's not the cardinality of an orbit. In general, it's not the cardinality of an orbit. So m is generally is lower bounded by n. Here, I mean, in this theorem, n, in any of the theorems, m is at least n, but it's not necessarily the cardinality of the orbit. In particular, in our case here, when we have the symmetric group, then m equals n, yeah, but the orbit of a generic point is of cardinality n factorial. Okay. Okay, so what happens now if we change from the complex numbers to the real numbers? Okay, why is what changes actually? And let's do again the simplest of all examples. Let's take the symmetric group S2, and let's take pi1 to be the first elementary symmetric polynomial. So that means x plus y, and pi2 to be the second elementary symmetric polynomial, x times y. Okay. Then obviously I claim the image of R2 under this map cannot be the whole of R2. Why? But why R2? Our ideal of relations is essentially trivial because we don't have any non-trivial relations amongst the generators. So the coordinate ring should be R2, or is R2. The coordinate ring is R2, but our map is not surjective onto that. Why? Well, I mean, look at this map. If we look at, for example, pi 1 squared minus 2 pi 2, then this evaluates exactly at the x plus y squared. And this entity can never be negative. So whatever we do, I mean, we can never map, we can never reach a point where this entity is negative. Well, and let's just look at this again in our setup of univariate polynomials. So I take small x and small y in R2, and I look again at the univariate polynomial t minus x times t minus y. So then again, by the very simple Vieta formula, this is just the first elementary symmetric polynomial times t plus the second elementary symmetric polynomial. And of course, a sufficient condition for a point A to be of the form x plus y and B to be of the form x times y and this x plus y is so that this is essentially reached by the map, by this map, so that it's in the image of this map is necessary and sufficient that this polynomial here only has real roots. Yeah? Because I mean the pre-image of the map are essentially the roots. They have to be real because we wanted to map from R2, and thus it's not very hard to see that essentially we only need to add this inequality here, which is essentially the one that we had already guessed before. Because this, by the discriminant of a quadratic polynomial, this has to be non-negative in order for the polynomial to have real roots. Okay, so that was so what we get from this is that the image of R2 in our case is not an algebraic variety, but it is a semi-algebraic set, so a set defined by some polynomial inequalities. And in fact, essentially, this generalizes easily to the case of the full symmetric group Sn. And all that we need for that is the following tool, which I call H of F. Some people H for Hamid. So it's a matrix. So when I start with the possible complex roots x1 to xn of a monic univariate polynomial f, yeah, and I set Sj to be the sum of the j's powers of these roots. So this is a symmetric polynomial. Again, this is what we call the Newton sum polynomial of the roots. And then I just define a matrix in this way. This is a Hankel style matrix. So I start with n here, then S1, S2, up to Sn minus 1, up to then I shift. I start by S1 here and go on, up to the last line where I start by Sn minus 1 to S2n minus 2. So for a given polynomial f, these are all some numbers because the roots are given. So this is an n times n matrix, and it's in fact a symmetric matrix. So at first hand sight, it might look a little bit odd because I start with a polynomial and I define the entries of the matrix by some operation that I do with the roots of the polynomial. And you all might know that roots of polynomials is not so easy to get a hold of. So how do we actually get this matrix? And this is one of the first things that you might have seen symmetric polynomials in an algebra class is that essentially these elementary symmetric, these Newton sums Sj, they can be expressed via the so-called Newton identities in terms of elementary symmetric polynomials. And the elementary symmetric polynomials, they are exactly the coefficients of my polynomial. So although I write this down in this very unique way, in this very nice way, essentially what you need to do to actually calculate this matrix for a given polynomial is to use the Newton identities to write those entries in terms of the coefficients of your polynomial. Okay, why is this matrix now important? So the interesting thing is, if I take a monic polynomial, then the signature of this quadratic symmetric matrix is equal to the number of real roots of f. And I mean, even if you forget about symmetry, if you have never heard the statement, it's a very beautiful statement because it lets you guess the roots, the number of real roots of a polynomial without the need of actually calculating the roots, just with linear algebra. And what do we get from that? I mean, in particular, if my polynomial has only real roots, then the signature of this matrix should be the rank of the matrix, and my polynomial, this matrix should be positive semi-definite. So we can now use this insight of monic polynomials to get to the following. So suppose I start with f0, f1 to fm. So now this here is really r to x1 to xn, symmetric polynomials in real coefficients. And I know that they can be expressed by some polynomials g0, gamma 0 to gamma n. This should be gamma n in some choice of invariants, but let's say, for example, the elementary symmetric polynomials. Then I can look at the problem maximizing f0 of x over Rn just by maximizing gamma 0 of y, where y now is a number in Rn. But I have to make sure that the associated Hankel Hermite matrix y, h of y is positive semi-definite. And equivalently, if I take a look at the system of equations, the real system of equations defined by f1 to fm, so the variety defined by them, there will be a point u in this variety, a real point in this variety, if and only if I can find a real point in this variety defined by gamma 1 to gamma n. But in order for this essentially coming from this, from a point u, I need to additionally make sure that this matrix is positive semi-definite. Okay, so the real orbit spaces are in general not varieties in the symmetric group case, but they are still defined by polynomial inequalities, because the condition that this matrix is positive semi-definite can be naturally expressed as polynomial inequalities. So what does this mean? I can use this above theorem, this above observation, and transform a polynomial optimization problem that is invariant into a polynomial optimization problem that is then defined with symmetric, I mean, with polynomials in my invariant ring, so with potentially smaller degree. However, I need to keep track of this Hankel matrix being positive semi-definite, so this adds some polynomial matrix inequalities in the invariant ring to my problem. And for example, I mean, if you know about this particular setup of polynomial matrix inequality can be neatly translated into the traditional moment relaxation approach. So the gain is then that one has potentially much less variables, because these degrees here, they grow linearly in n, and these polynomials might have a smaller degree. Then I have less variables to care of in the invariant ring, but I have the price I need to pay is I need to make sure that this polynomial matrix inequality is satisfied, but this I can do with some sort of Lasserre hierarchy. So let me just mention that this essentially, or let me just say what variety that is complex or real. So the variety is real. The variety is real. Yeah. So B, it's supposed to be the real variety. So I want to find. So essentially, this is the real variety. I look at the map pi, and the image is essentially the points in this variety that additionally satisfy this. How does this now generalize? This essentially generalizes, and just for your this is a little bit quick now, but there's a very nice generalization, and this works as follows. I just look at differentials of polynomials, so forms of like this, dp, and I define, and we already saw that on Rn I have a G-invariant scalar product. Now I can take this to these differentials and just define this product of differentials here, the scalar product, and this is an invariant product. So whenever I take my generators pi1 to pi j and take this inner product of their differentials, I get a G invariant polynomial. Okay, and now I look at the matrix where I put all the possible pairwise scalar products of the gradients essentially of my invariance pi1 to pi m. This is then a G-invariant matrix polynomial, because the entries in generally are polynomials, but they are invariant with respect to the group, so I can represent them with my pi1 to pi m again. And then this is in fact used to describe the real part of the orbit space. Namely, there's a theorem by Procesi and Schwarz from the 80s that tells you, this even works for complex matrix groups, but in our setup, of course, a finite group is also complex. So the orbit space, the real part of the orbit space, so the image of pi, the image of Rn under the map pi, this is just all the points. So this is a map from Rn to Rm in general, yeah? And the points are all the points in Rm that lie in the variety defined by the algebraic relation of my generators. But additionally, they need to satisfy that this polynomial matrix inequality is positive semi-definite. Okay. So let me give you. This was maybe a little bit a brief introduction to orbit spaces, but the takeaway home message for that is just that the geometry of these orbit spaces can be used to see and visualize the symmetry reduction that we have been seeing last week again already, namely the restriction, the map that we take by replacing our initial polynomials with the corresponding polynomials in the invariant, in the generators of the invariant ring. However, one has to be very, this works very, very canonically over the complex numbers. However, if we are working with real polynomials and we want to talk about real solutions, then we have to be a little bit more careful. However, this previous theorem tells us that there is a canonically defined, or not canonically defined, but a very nice defined semi-algebraic set that we can use in our reformulation to get this. And in particular, our polynomial optimization problems can be transformed into symmetry-reduced problems with polynomials that do not have any more symmetry, because we essentially factor the symmetry out over the image of this map pi. And the price we have to pay if we want to do this over the reals is we have to add a polynomial matrix inequality to that. Okay, so as I decided that every good story should begin, and not every good story comes back to its beginning. That's maybe a little bit too positively thought, but at least I thought that because I started with this image, I should to some extent come back to this image a little bit again and use this again to motivate the second part of this lecture today. So remember, I showed you this image in the first lecture, and I told you that this doesn't maybe make much sense to you, but it makes much sense to me. But that's maybe true with a lot of things, so don't worry about this. But I want you to keep in mind the following thing again, that complicated looking things, like this picture, can be easily understood by understanding the symmetry. So here the symmetry is given by these walls, understanding the symmetry structure, and then only focusing on this smaller part here. Okay? And essentially now I want to make this in a different way, a little bit visible again. Namely, I want to ask, how complicated can sets look like that are defined by polynomials, in particular by symmetric polynomials? So what kind of picture can we get, and what kind of picture can we get in the interior of this fundamental domain, this orbit space? So how complicated can a semi-algebraic set be? Okay, so suppose you're given a finite set of polynomials, script p, and one can consider the real variety defined by those polynomials, or more generally, any semi-algebraic set which can be described by the polynomials in this finite fixed set pi. So, so suppose, because I'm not a good painter, I could never paint such a picture that I showed you previously, but I'm a mathematician, and mathematicians draw pictures, geometric pictures, by prescribing, defining equalities and inequalities. And how complicated can a picture look like that I can describe with the polynomials p that I maybe have set aside for myself? So now it's a little bit vague. What do I mean by the complexity of such a semi-algebraic set? Well, one standard notion of doing this is with the so-called Betti numbers. So for the people who know what the Betti numbers are, then this is essentially the definition. They are the dimension of the homology groups. But a good thing to remember is the zeroth Betti number is in particular the number of connected components of my set S. And what does this have to do with the complexity of a set? And because some of our some people in the audience, including me, are interested in optimization. Well, the more connected components, for example, a set has, the harder it is essentially to optimize over such a set. Why? Because if you think about, you take a generic function that is rather nice, even maybe a linear one, take a linear function that's rather easy. If your set is connected, has just one connected component, the number of critical points that your function will have is rather small. If you take a linear function, it should be, if it's a generic linear function, it might have only one global maximum or one global minimum, a local global minimum maximum. However, if your set has a lot of connected components, then for every connected component, you might get an additional critical point. So if your set is very wild, has many connected components, then it becomes much harder to optimize over the set. And this is in generally true also with these higher Betti numbers. The more the wilder your set looks like topologically, the harder it actually is to do something with that. Okay, and I want to now get some estimates of this number in terms of the number of polynomials. I don't really care about the actual polynomials. I just say the number of them is fixed, the degree of them is fixed, and the number of variables is fixed. Okay, so this is a very, very classical question, has been first studied in the 50s, 40s already by Petrovsky, Cordian, Tom, and Milner. And the classical bound that you see here is, if I have a variety defined by polynomials of a given degree d in n variables, then essentially this quantity is bounded by something that is exponential in n for a fixed d. Yeah? And this bound is more or less also sharp. And more generally, this was also generalized to semi-algebraic sets. So you have a similar looking bound that was found by Basu, Pollack, and Roy. That is, if you fix the number of polynomials and the degree, then it's something that depends exponentially again in the number of variables for fixed sizes of d and s. Okay, so why do I care about this? And I try to already motivate this a little bit, but there is a sort of belief that was maybe justified by what I said about optimizing over such set, and that's that the worst case topological complexity of a class of semi-algebraic sets, if we measure it with these Betti numbers, with the sum of the Betti numbers, for example, they give you a rough lower bound for the complexity of algorithms that you need, for example, to compute topological invariants or decide topological properties of this class. And that's essentially what I told you previously. If I have many connected components, then even if you have a nice function, I mean, like a linear function, it might be very hard to calculate the global minimum, the global minimum of this, because I need to go through all of the connected components individually. And just to motivate us further, I mean, in the quadratic case, I mean, we know that quadratic optimization is easy. So quadratic, I mean, you have quadratic constraints. So quadratic semi-algebraic sets are much more easy to handle also from the optimization point of view. And essentially also there one has, as a result of Bar-Vinoch, one has good bounds, meaning polynomial bounds in these cases. So why did I want to interest you into that? Because, I mean, we have seen last time already that if I take symmetric polynomials in n variables for a fixed degree d, then I had this neat small theorem that I told you, that I showed you last week, when we can only reduce to when we already can prescribe the symmetry of the minimizers and thus reduce our problem in n variables to problems in d variables. So in particular, we could decide if a polynomial, if the variety defined by one polynomial is empty or not. We can efficiently maximize or minimize a given function over that. So the question that one can easily ask is, does this actually mean that the topological complexity measured by these Betti numbers is better? So let's just look at a very simple example of that. Let's look at this polynomial. So this polynomial is a polynomial in n variables. It is symmetric. It has a degree d. That's essentially what we have. And if you want to stare at it for maybe a minute or two, you will essentially see what kind of variety is defined by this polynomial. Well, it is just all the points in the real n space that have coordinates in this set, so that whose coordinates are either 1, 2, 3, up to d half. Okay. So how many such points can we find? Well, there are d half to the n many such points. They are all isolated points, so this is essentially the number of connected components of this variety. So this is an exponential growth. So at the first sight, it seems that this topological complexity that I defined to you behaves as badly as it did in the non-symmetric case. So, but now if we do something very simple, if we only look at, instead of all of the points, we only look at those points. We identify points that are in the same orbit, so we only look at the orbits. And then, I mean, we essentially see that if we look at this quotient, well, I mean, all the points are, are in the same orbit. If I can order them, if I can order their coordinates in an increasing way. So I put first the 1s here, then I put the 2s here, and so on until I put the d halves here. So the orbits of my polynomial of my points are uniquely defined by these parameters t1, t2 to dn minus d half that give me all the ways that I essentially can distribute the numbers 1, 2 up to d half up to symmetry onto these n slots. So how many of them do I have? Well, this is another easy combinatorial exercise. It's essentially this binomial coefficient here. Okay, and now if we assume we fix d and just care about the asymptotic of this quantity in terms of n, then this is a polynomial. This is lower bounded and upper bounded by a polynomial in n of degree d half minus 1. Okay, So essentially, I mean, this was an easy example, and most of the time, the easiest example that you can come up with is essentially the generic example, and this is also true here. So essentially, one can generalize this, saying that if I take not only the connected components, but essentially the sum of the Betti numbers, not of my semi-algebraic set, but of this image under this quotient map. So up to the action of the symmetric group. So to really define this is a little bit hard now, but just think about, we count points up to symmetry here. Then this is something, this is a quantity that is bounded, again, D and S are fixed. This is something that is bounded by a polynomial in n of degree d half minus 1. And what is maybe interesting for the experts that know a little bit more about homology is that also the higher homology groups, they essentially vanish. So in some sense, if you know what this just means that our quotient, not the set itself, our quotient behaves as if it were a variety or a semi-algebraic set defined in d variables instead of n variables. Okay, and the trick to actually prove this theorem is essentially very much coming from the theorem that I stated last time, namely, we know already that these sets always contain points that have a very special stabilizer, and then one needs to show that one essentially can reduce our quotient to these sets by retraction. Okay, this may be a little bit too much for you if you have never seen about homology, but you know, again, this is maybe also interesting. This is a sharp result, of course, because we have seen that this exponent is best possible because already our easy example that we had in the beginning turned out to actually meet this bound if we only look at this exponent, for example, of course. So this is essentially the best that you can hope for. But it sort of shows that although we have a very, very wild picture in the sense of we have many connected components, when one only looks up to symmetry, so only restricts into this fundamental chamber, the picture becomes much, much easier to understand. So here we only need to calculate, these polynomially many potentially linear critical points of our linear function. Okay, and I mean, this is another interesting thing, of course. This then in the setup here also calculates, translates in an easy algorithm to actually compute those numbers if you're interested in that. But this is maybe not so important. More important is that, I mean, the second step is also interesting, but turned out to be much harder. This is also just a remark. So, I mean, suppose again, you're looking at this picture here, and you were in the museum, and later your partner or your grandmother or whoever you talk about art with asks you to describe the picture, but you only remember this small part of the picture, then of course it's a non-trivial task to come up with the whole picture again, even though you need the symmetry, you have the symmetry. I mean, you still need to know how the symmetry essentially acts on this smaller picture. But also this can be done in some cases. So in particular, this is again maybe interesting only for some. One can calculate the Euler-Poincare characteristic of S and also the first L-Betti numbers in a reasonably efficient way. Okay, so this might have also been a little bit just a taste of something, but I think this gives a nice example for the second take-home message that I want to give you as a sort of conclusion of this whole series of 3 talks. And this is that many complicated problems have inherent symmetry. So like this beautiful picture that I show. And in fact, this symmetry, this is something that is maybe just a philosophical belief now, but in fact, this symmetry might be one of the reasons why the problem looks inherently hard. Because many of these components might be only inherited from the symmetry. I mean, this is not necessarily the case, but it makes a little bit sense because, I mean, in some way, if you look at a problem that is given to you and you can actually read the problem, then this means that the problem itself must have some structure that you can actually read before you can go to solve it. And such a structure might be the symmetry. So it's inherently hard. However, you have a vast toolbox of different tools, from invariant theory, representation theory, or geometric invariant theory, orbit spaces at your disposal to simplify such problems. So for today's lecture, let me just once again mention some topics from the literature that you might find interesting if you want to know more about these toolboxes. So there's a beautiful book by Sturmfels called Algorithms in Invariant Theory that actually talks about the computational part of all the beautiful things that I talked about, because as you might have seen in my talks, things fall from the sky somehow, and it's not clear how you can actually get hold of these generators, for example, but there are algorithms to do that, and some of them are described in the book. Then I mentioned this result by Procesi and Schwarz. This appeared in this article defining inequalities defining orbit spaces. I also mentioned this possibility of reducing symmetric, so invariant optimization problem into an optimization problem over this geometric quotient. So this is also a little bit more detailed, described in this article here. And I gave you as a small taste at the end this picture equivariant Betti numbers. So this is just exactly meaning we calculate the Betti numbers up to symmetry of symmetric semi-algebraic sets, and all the results and a little bit more that I briefly discussed in the end are in this paper here. So I actually want to close not only this lecture today, but the entire lecture series. And what's better to close something than having people that are definitely smarter than me saying something. So I want to close with this quote by Hermann Weyl that says that symmetry is a vast subject significant in art and nature. We saw art, we will also see nature. And mathematics lies at its roots, and it would be hard to find a better one on which to demonstrate the working of the mathematical intellect. I hope that you were able to at least get more understanding of the beauty of symmetry and its significance, not only in art and nature, but also in polynomial optimization, and get some of the ideas why mathematics lies at its roots and how one can actually use mathematics to simplify problems that are symmetric. But more importantly, I hope you all enjoy the summer break, and thus I added a small picture of nature around here, a little bit less symmetry, but maybe more beauty even here. Thank you very much.
So thank you very much, everybody, Cordian. I see there was a question by Alejandro Gonzalez Navarro. It was about the exponent and the bound on the Betti numbers, I think.
Let me see what this is. 16. Yes. Is it possible to make n any smaller? No, in general not. In general not. I mean, if I understand the question correct, these bounds are from the exponent point of view sharp. So in particular, I mean, the example that we have here, yes, I mean, this is an example, right? That's the n is essentially in here. I mean, this is the easiest example, and it's exponential in n. I hope this answers the question, if I understood it correctly.
So I just give everybody a few seconds to type. Last time it took a little while before the questions started appearing.
Yes. Yeah, let me just, as a teaser maybe to everybody who's never been to Tromsø, this is, I mean, not in Tromsø, but not very far from Tromsø, where you just need to do a small hike, maybe the 3/4 of an hour, and you have this astonishing view into the fjords and to the mountains of Norway. So yeah, if you ever get a chance and interest to visit Norway, then I'll definitely forward the coordinates of this place to you.
So while we still wait, Cordian, maybe I just mentioned, you already said about the break now in the POEMA Learning Weeks. So we will only reconvene again on September 2nd, if I'm correct, the first lecture by Professor Mihai Putinar. Yes, 2nd of September, same time. So we have a break for August and the rest of July. Okay, thank you, Monique, for nice words.
Yeah. So again, of course, I can just say that if you have questions, feel also free to send me the questions by email. We can discuss. And some people have already sent me questions by email, so there's no rush for you to shoot them out now if you want to think about them. Again. Enough food for thoughts, yes.
Yes. Okay, Cordian, we don't seem to have more questions, so let me just thank you again on behalf of everybody. I can only say for myself, I learned a lot, and I will be one of those sending you email with the question. But I'm sure the same is true for many of the other participants. So thank you very much for these very interesting lectures. And so for everybody else, thank you for joining and have a nice summer. And we hope to see all of you or most of you back in September. So thank you very much.
Thank you. Bye-bye.
Bye.